would be very shocked if this works. Wow. I am very surprised that worked. Oh, I don't have shadow. I was not expecting that to work. Okay, so I guess we kind of have to do stuff. Okay, let's try this. Being stupid. Don't expect. Being stupid. Why is this being done? Oh. Why is the header guard not doing anything here? So what it's doing is it's going here. And then, yeah. Why is that happening? Figure it out later. Fucking figure it out later. Sanity check. Yeah, I've no idea. I mean, I have a slight idea, but I don't feel like dealing with it right now, so. I need to do... Right. I need to do this fucking... Actually dumb as bricks, dude. This JIT doesn't have an entity handle. Figure out why this is happening, because I don't know. Alright, fix that, naturally. Oh. What is this shit talking about? Oh, I still need to include game state. Oh, it doesn't like the types. Uh, I mean, Oh, I don't think I ever called it init function anywhere. That shit pissing me off. Okay. Is there not a way to do this where it just populates via a null pointer? Does throw an exception. Oh, I don't want to throw an exception. I just want to fucking get my shit. And if it's I want to like make a point. Okay. That's why the fuck would they, right? So that works though. Oh, I just realized this solution only lets you have 64 of every entity. This needs to be that. Not even. This needs to be. Wait. Why would you buy it? What's going on? This feels fucked. I don't think I was thinking when I wrote whatever this is. Hold on. Like back up. Yeah, this was terribly misguided. Oh, whoa, wrong direction. This is a what do they call it? I don't even know. This is bad. I don't think I'm allowed to do this. Alright, I'm returning a stack pointer. That's illegal. And I guess I could try it because if this doesn't work, I'll just use an index. But I'm like 95% sure that this is like the biggest no-no you can make in C++. But I'll try. I'll bite. I'm just gonna leave it in the header for now. My dumbest bricks, this should give me pointer to block. Empty blocked, empty block. Or am I doing that? Oh, it's in the return type. Maybe? No. Oh, I think it wants to be this. I'm pretty sure this needs to be a const and a constant reference. Yeah. But this can't be constant. Yeah, no, that's not gonna work, unfortunately. No, because it's just gonna be a bad return type. Yeah. Fine. Try to be fancy. Try to be fancy. Not looking like it's gonna work. I mean, I could do. Oh, could I do this? Hold on. Hold on. Hold on. Hold on. That might work. Not convert from constant entity block pointer to a regular entity block. Stop. So this needs to be a constant reference. This is not. Yeah, I'm just gonna do it the fucking not fancy way. Give up. You win. It's blocks don't count. What is the... Oh, it's size. Of course it's size and not something that actually makes sense. What? Oh, we're getting fun template errors now. Is it like the compiler yelling at me because this always returns an opener? Since the compiler's fun way of yelling at me. Yo, OpenGL is a rendering library. Basically, it is a bunch of pre-built code that helps you put shit on the screen. So I'll show you now here. If I compile with like actually functioning code, OpenGL is what lets me put this on the screen. Basically, it's the way I would describe it best. Actually, is it's code that lets you talk to your GPU, to your graphics card. Better example of something like that would be my other image in a different language. So like CUDA, I've heard of CUDA, but I don't know what it is. Yeah, like kinda. It's built for rendering, but you can do they're called compute shaders, which is basically this. Despite having the name shader, it's just a parallel processing, which is what parallel computing. Yeah, so it's kind of like that, but for rendering specifically. Oh, it's giving me some bullshit. I'm assuming it's some. One or more. Oh, did I call something the same thing? Here, chill. Line edit log, any logs. Yep, okay. Do I have find available entity block defined twice or something? Let me, so this should have nothing to do with that. If I just... Okay. Now it might yell. No? Okay. I guess I was just being stupid. It's really typed out these structures, but I really don't feel like it. Okay. So what we can do is if the box I dot if the member mask equals all ones is full. So this is if it's full. So rather we would want to do if it's not full. Because if it's full, we don't want to do anything. If it's not full, then that's the one we want. We want to set to I have a struct function. Because I didn't type def the structure over here. I could do this. It returns a struct object pointer. I could do this. And then I wouldn't need to do this. I could just do this. But I didn't want to do that because I got lazy. I mean, I just did it, but... Then I would have to go back and do it for all of them, just for consistency's sake. I didn't feel like doing it. Is that a Persona 5 profile picture? I can't tell. I can't tell. Okay. I don't think that returns like a reference or anything like that. I think if I wanted to get fancy, I would have to do pretty sure that's it. Binary plus is not minus operator. No, I mean like not for like Minecraft blocks. This is for entities. It's like I guess I should describe what I'm doing. I built this system already in Jai, but Jai has fancy like compiler bullshit that made this like a joke. Oops. Again, the fact that this is voxel engine has nothing to do with like Minecraft chunks. The way I'm doing it here, I like to explain this because the code here, this code in this Jai project is the code that's in my banner on like everything. I just think it's pretty code that I wrote a while back, and I'm writing the ugliest C++ version of it. So the way that I'm having it work is basically the like entity manager has like a list of a bunch of these blocks of memory. So basically I get the size. So like let's say we're making an entity. So like I want to make a new entity. Like the first thing you got to do is get the size of the entity. So let's say the size of the entity is like, I don't know, like 12 bytes. So this is in bytes. Then what I'm gonna do is I allocate 12 bytes to the size times 64. So inside of this like block, I allocate 12 byte blocks. So this would be like 12 bytes, and this would be 12 bytes. This would be 12 bytes. And I do this 64 times, so it's 8 by 8. And then I also have an unsigned 64-bit integer called the member mask. And basically the member mask says, like, I guess in this example, we'll just pretend this is 8 by 8, but actually no, don't. It's 4 by 4. We'll just, for this example, say it's 4 by 4, right? And this goes on and on. So I have this, in this example, it would be 16-bit member mask, which is 0b. I guess this would be easier to type, wouldn't it? Be like 0b. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And each 0 beyond the B responds with one block that I allocate up here. So basically, every time I want to make a new entity, I would go through each of the blocks, and then I would say, okay, are you available? And it's like, oh, look at that, it's a 0 here. You would do a bit scan forward, so we over here, like, oh, look, or an inverse bit scan forward. You would flip all these to 1s, so you would actually have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And you would look from the right hand side, you'd be like, oh, there's a 1 here, so because we flipped it, therefore the spot is empty. So you would do 0b, 1, 2, 3, 4, 5, 6, 7, 8, 9, I can just spam actually, until you get here, and then you flip this to a 1. So now this 12 byte block is full with some entity, which means we can't allocate it there anymore. And then basically the idea is that when this is all filled up, it will look like the first one. It will look like this up here. So then it's like, oh, okay, it's all filled up. Make a new block with, in this case, 16, but in practice, 64 new member slots, right? So the reason I have it like this is so that you're not just like allocating small portions of bytes intermittently throughout your program memory. Like, that's kind of cheeks. I would rather have them grouped up like this. The problem with this system, though, is every entity is going to be a different size of bytes. If you do a union struct between entity and, you know, your extension, right, that's like abstraction, now your 12 bytes are different. And this whole concept doesn't work if this is 12 bytes and this is 16 bytes and this is like 243 bytes. Like, that just doesn't work. So instead, what I'm doing is I'm using some, I like hope, some C++ compile time bullshit that lets me get a type. I can pull this up in the code, right? This here. So I can pass in a type and get its type info, and I can get a hash code, and this is completely unique for each type. And this should be executed at compile time for every type, so this should basically cost nothing. And then I have an unordered map that maps the hash code to the vector of entity blocks, so that way every entity basically gets its own pool of blocks. So if you have a really big entity that's like, you know, 234 bytes, you can say, okay, that gets its own chunk of memory, and like, that's going to be huge. But my thought process was most computers have more than enough RAM to like make that reasonable. Like, I'd rather expend a little bit more RAM being redundant than have your CPU be slow and allocate this memory every single time you want a new entity. Like, that's gonna suck. You won't be able to create entities like this. What's the fin? I don't know what that means. But yeah, I would say it's a chunk system, but more so for like entity pooling, entity memory pooling. Because like, yeah, I could very easily just do this. Oh, do that. Oh, Jesus Christ, I like actually am retarded. I could just do that, right? And there would be absolutely no problem. It's just, right, if you have your program memory, you know, if you have your heap, it looks like this, and then you make an entity. You're gonna have one entity over here, and you're gonna have one entity over here, and you're gonna have one entity over here, and and then like, here's your shit, and like, kind of pretend, you know, it's blocked off like this because this is how the heap is gonna do it. It's gonna go here, 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 right? So there are your entities, right? And now, okay, we're loading in the level, and we need to load in like 200 kilobytes worth of vertex data, and the heap is gonna go, oh, I can't allocate that much. That's like this much space, but look at how much crap were filled in. So it's gonna go, okay, now we gotta move you. Oops. It's gonna be like, now we have to move you over here. And you. I mean, it would do a better job at like packing them together, right? So it's gonna move all this crap. And it's gotta do it one by one, because it's gotta find shit that can be moved. It's gonna go all the way over here. And then, finally, the operating system's gonna be like, okay, I have enough memory to, you know, make this giant thing. And it's just like, eventually it's just gonna be a pain in the dick to manage all this. I mean, we don't, as programmers, have to manage that, but you can imagine if you, let's say you want to spawn bullets, and each bullet is an entity, and you're firing like 60 rounds a second. Not even, you're firing like 120 rounds per second. I'm gonna do this each block in a way that doesn't waste memory. Yeah, pretty much. I mean, it's gonna waste memory. It has to. If, let's say you have a unique entity that literally only one of is going to exist at a time, you're allocating 64 times the memory, which is like, somebody would be like, what the actual fuck? That's like ridiculously redundant, and I would agree, but it's just infinitely faster on the CPU. Like making multiple new calls a frame, especially for something that's gonna be 20 to 30, you know, bytes, it's gonna cause a performance hitch. Like, it's just kind of out of the question if it's gonna do that or not. It is. Just can't happen. So again, I did it here, but what's nice about Jai, I love talking about Jai when I get the chance, is you have these tags, this structure tag, and basically what I can do with that is this function here, where at compile time, I go through the entire program source and I get every structure that, it's not called a tag, it's called a note. I get every structure that has this note entity, and then I get its size. So I get the largest size based on all the entities. And then what I can do is, instead of doing this whole bullshit where I have an unordered map where the key is the hash code of the type, and then the value is a reference to a vector, like, that's so bad. That's just absolutely deplorable code that I'm writing right now. Instead, I just have this neat little, I just have one array, and that array, the size of each element in the array is always the largest size per entity, which is, again, a lot of redundant memory. But the CPU just chugs through these. Ooh, I'm getting a phone call from one of my programmer friends. I thought he was watching the stream and he was gonna like yell at me for like being a bad programmer, but he just called me for some bullshit. Oh, that just tweaked me out because I thought I was missing semicolons here. Anyway, again, so fancy compile time Jai bullshit. It's really nice. So I get this max here, and then in the entity block I have this void pointer, and then when I create an entity, like I said, you do a bit scan forward on the inverse member mask, -1, because if you find the first bit that counts as 1, it's not indexed to count. So you subtract 1, you bit shift over, and then each entity has an ID, which in this case is U16, and I'll probably make that a U64. And basically, for scientific purposes, the way I see it is, so we'll pretend it's a U16 still, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Basically, if you 1, 2, 3, 4, 5, 6, 7, 8, right in the middle here, You can kind of think of this U16. Imagine if this was a U64, you'd have 32 and 32 rather than 8 and 8. This first word here, I guess is what you would call that. Oh no, sorry, this first byte. This first byte corresponds to what slot of the member mask you're in, and then this one is the index of the block you're in. So if you think about it, this is the block. So it's just an array in the Jai version, which is what I'm trying to represent here because it's a much cleaner version of this. This is the index in this array. So which block you're in. And then this is the offset from the beginning of the pointer. That's calculated by a bit shift, I believe, if I recall correctly. Yeah, right. So you split it up. It's the slot mask. Yeah. So you get the memory, and then the right app of this is the offset. And with this, you have a unique identifier that will, in theory, never, actually definitely not, it will definitely never ever be shared with any other entity. And it's not arbitrary either, so double, in theory, you could run this program forever, constantly making and breaking things, and you'll never have an overflow. It always just makes new memory. I wouldn't say it's infinite, it's just because you have 32 bits, so eventually you could fill up 32 blocks worth of memory, which is like an absolute, not 32 blocks memory, it's whatever the 32-bit unsigned integer limit is, which is like in the, a number so unfathomable, it's 2 to the 32. I don't even know what that number is off the top of my head. This, and then times this by 64. Where did you learn about memory management? Honestly, kind of word of mouth. When I got invited into the Jai Discord server, they just kind of anticipate that you know that. So I just kind of asked around, and people kind of taught me what I know. It's very simple. It's like, I hate to say, like, when you think about it, it makes sense, because that implies that, like, the people who don't understand it, like, aren't thinking about it. But, like, you just think about it's a heap, it's just a pool, right, of memory. And you have two different kinds. So you have the stack, which looks like this, and then the heap, which looks kind of like this. And when you put things on the stack, it goes from the bottom up. So you got a thing here, and then you got a kind of a bigger thing here. And then you got a bigger thing, or maybe a smaller thing here. And it's like, oh, now we're done with this thing. So we just pop it off the stack, and now we're done with it. Now another thing will go here. And you can't rearrange what's on here. So that's, if you've ever heard of a stack overflow. Let's say you're just like, every time you run a function inside of another function, all of that function's garbage goes in the upper function stack. So you can have things that kind of fill out here. And you can resize this. It's just not easy. And eventually you may fill up so much of your stack memory that you have something like this, and it's like, oh, stack overflow. Right, so that's how you do that. And then every time you use the new keyword, or you have an array, at least a specifically heap-sized, array, like a vector or something like that, you kind of allocate over here. And just think about if you have like a bunch of Legos or something, and you're trying to fit them all in like this. Like, now you have this giant Lego, and it's like, well, where the hell am I going to put this? There's nowhere for me to put it. But if you organize all your Legos in your bin from the start, and you kind of put them all in the same place, even if it's redundant, like, let's say you only need, this much worth, like, this much worth of, oh my god, this much worth of memory, right? It's so much easier for your operating system to handle. You just kind of do this, and you say, okay, I know I'm only going to have up to, like, that much, so you can start putting it in here, and it's very organized, so I don't want to just draw them all over the place, but something like this, right? Now it's so much easier for you to fit your big Lego in here, because everything, your operating system understands that everything you're going to put in here is going to go in here. That's kind of how I think about it. Pointers, I like watched a YouTube video. I didn't think they were that difficult, and I'm not like some prodigy. Like I'm honestly pretty retarded. I just right. You have your right. So remember, we had this. This is your memory, and then somewhere in here, right? Here's all of our shit from earlier. Right, here's all of our stuff that we've allocated in our program. And the operating system is smarter than this, so it's like not this haphazard, but like if you think about it like this, you'll write better programs. The pointer just points to like some offset from here. So if your pointer, let's say your program memory starts at 0, 0, or at just 0. It doesn't, but let's say it does, which is like up here. If your pointer is at like, I don't know, x45. I'm just making shit up. It doesn't really matter. It's just some offset from the beginning of your program memory. Fuck. I have to go. Damn it. Oh, I was in the middle of such a good explanation. Okay. I gotta bounce. I was not expecting that. I will